But the best part was that we didn't even predict the population. It was like, let's just put three. No. You weren't supposed to be disappointed or not. Yeah. Horrible. We get anything? Okay, so, the thing was $425. I think that'd be.
You're gonna have fun. Kelly, you can go. You're gonna have fun. You're gonna have fun.
Like I say, it's super growing. I can do that. I guess I'm just sitting down.
What's up?
We're working on the project one.
All right.
And in
What?
project
Yeah.
two, project
Okay.
two.
Yeah.
And in calc energy,
Yeah.
you're storing the gradients in, or it's said to store it in struct star gradient. Like
Yeah.
RGB image gradient.
Yeah.
But in the struct, there's no variable name like gradient. Are we supposed
No, like that's a variable. Right? Make a variable.
Oh, okay. You just outlet like say create image.
That makes sense. Thank you very much. Okay. Okay, let me start. Yeah, sorry about that. Okay, so so at least people are listening, so that's good. So I'll start from the beginning, which was just saying that I'm going to talk about Dijkstra, and I'm going to talk about finding the cheapest path. Sorry, this is the wrong. Yes. So we're talking about finding the cheapest path from the source to any one of the destinations, and we're going to compute the cheapest path from the source to every destination. So for example, the cheapest path from A to E is through B. So the cheapest path is 2 plus 1. Okay, so that's the goal. So for every node that's not the source node, for the source node, we know that the cheapest path is 0. We want to compute the cost of the cheapest path. Okay. So, all right. So the idea with Dijkstra is we keep a set of visited nodes. Initially, it's just the source node. And then what we do is we say, if we step outside the visited nodes, what's the cheapest thing that we can add, where we're going from A somewhere inside the visited nodes and then jump outside the visited nodes. And then we record the path. And like we argued last time, that will actually be the true cheapest path if you add the nodes, if you visit the nodes in this order. So here, so far, the visited nodes are just A. And the cheapest way to step outside the set of the visited nodes is to just go to C, right? Because that costs 1. So we visit C, and we record D of C as 1. With me? So, okay. So now we just repeat the process. So visited nodes is A and C. And we want the cheapest node to add with the smallest possible distance, total distance from A. So that means that the candidates are B, that costs 2, or D, that costs 6, or E, that costs 4. Right? So to add E costs 4 because it's 1 plus 3. B is directly connected to A, so that just costs 2. D costs 6, so B is the cheapest. And we can now say the distance to B is 2. So what do we have now? So we now have E. That's 2 plus 1. So B is already visited. So we can jump from B to E. We also have the option of going from C to E. That's going to cost 4. And we still have the option of going to D. That costs 6. The smallest one is 2 plus 1. And that was like the first non-trivial one. So we recorded that the cheapest path to E is 4. Right. Is 4. And that wasn't obvious because sorry, that's not true. It is 3 because 2 plus 1, right? And that's not obvious because, there's 3 possible ways to get from A to E. And because we are adding the things in the order in which we do, so cheapest path from inside the visited set to outside the visited set, by theorem, that's actually going to be the cheapest path. Yeah, even though we haven't explored everything yet.
Say starting from inside the visited set, is it really starting from A specifically?
No, it's starting from the visited set, but the cost is recorded from A up to the node that we are adding. right? So that was the last example, right? So B was in the visited set. So we were allowed to go from B to E, but then we record the cost as whatever was the cost to get to B plus the cost to get to E.
But we're looking for the cheapest cost starting.
That's right. Yeah, so we're looking for the cheapest total cost starting from E. Yeah. Because C was cheaper, right? So going to C cost 1. So that was the first node that we added. Well, we are adding things in the order in which is specified in Dijkstra, which is cheapest path from A through the visited set to the new node. So we can now consider the candidates. So we've added E, we've just added E, right? So now what are the options that we have left to go from A, C, B, E somewhere else? Well, we can go to D, that's going to cost 6. We can go to F, that's going to cost 10. And we can go to G, that's going to cost 8, right? So, okay, so D is the cheapest. So at this point, we're going to go to D. And that's going to be 6. At this point, the options are, so we visited A, B, C, D, E. And the options are either go to F or go to E. So F costs 10 because getting to E costs 3. And G costs 8. So that means that G is next. And G is over here. And now we can go to, so now we can go to H. H is going to be 8 plus 6, so 14. Or we can go to F. F is going to be 10, so we're going to F. And now really the only thing to visit that's left is H. So the question is, which way is cheaper? So D of G is 8. D of F is 10. So we are taking this edge. And we get D of H is 15. Okay. And at that point, we're done. So the magic here is if we're adding it in this order, so we're jumping from the visited set to a new node, then we get to record right away the cost. Yeah. D of H, no, it should be 15. So it's 3 plus 7 plus 5.
Plus 5 plus 6.
Why is it? That's yeah. Sorry, yeah. So it was cheaper to go through G actually. Yeah, 14. Yeah, thank you. Yeah. Okay. Yeah. So the reason was that D of G was 8, and 8 plus 6 is smaller than 10 plus 5. So yeah. So that's better. Thank you. All right. So that's that. So now let's look again at the algorithm. And this is just the algorithm that I just described, right? So we're saying initially we record the source as 0, and then we keep adding stuff to the visited set S. And the way we add them is we find a node we find a node U such that that's inside S such that du plus uv is as small as possible. Okay, so we find something in the visited set where we can jump to another node that's not in the visited set, such that getting from the source to U plus the cost of the edge from U to V is as small as possible. Yeah.
So I guess like in the example, we have to consider when we have multiple ways to get to the same node, right?
Yeah. Yeah. Okay, so that's it. So that's the basic algorithm. So here's the so the only thing that's left is if you want the actual path, then what you can do when you're recording how much it costs to get to V, you can also say for the cheapest path to V, you need it to go through U. So you just record like, before V, I'm at U, so that you can then recover the path. Yeah. Yeah. So this is the graph that consists of vertices and edges. Yeah. Okay. Okay. So that's it. So I now want to talk about a more efficient implementation, if you can have an efficient implementation of a priority queue. So this is the original algorithm, right? So what this algorithm requires is basically looking for every possible candidate for the pair UV every time. So that's expensive. But what you can say is when I visit the node U, I guess, for the first time, so then it's called V, right? So at this point, I'm choosing the V that I'm visiting. What I'm going to do is I'm going to look at all the neighbors of V and say, if I were to go through V, this is how much it's going to cost me. And I'm just going to record that every time. And then if I maintain it as a priority queue, so I maintain, okay, like if I go through V, this is how much it's going to cost me. And how much it's going to cost me would be my priority. Then I can ask my priority queue, hey, like, what's the neighbor that you've added for consideration that's the lowest priority, meaning the cheapest to get to? Just get me that. Okay, so instead of looking for every possible UV pair every time, I'm just going to query my priority queue and say, what's the neighbor that you've already added that's the cheapest to get to? Because that's the same question as what's the UV that corresponds to the cheapest sum DU plus the edge UV. Make sense? So let's do that. So I'll start with kind of the slow implementation of Dijkstra, which is over here. So here, I implemented things slightly differently from before and actually considered like reformatting it to graph 2. And then I thought it's actually good to see multiple implementations of graphs as well. So here what we have is we have a node. So the node has a value and a node has a set of has a set of connections. And then because I'm specifically running Dijkstra, I also am going to record the distance from the start node initially as infinity for this node. Okay. And then a connection, it's just going to be stored as a list of connections. A connection is like a struct that keeps the node and it also keeps the weight. Okay. So here, so this is kind of the simple Dijkstra where what they say is, okay, so I start from node start and thank you. So I start from the node start, and here I'll just terminate if it turns out that I see the node end. If I don't terminate, then I'll just compute the distances to all the nodes in the graph. And here I'm saying, okay, so for every node in the visited set, go through all the connections, meaning go through all the neighbors. And then if it's already visited, then doesn't matter. If it's not visited, then look at whether for this node in visited, the distance from start plus the weight of the current connection is smaller than what we've seen so far, and eventually just add the minimum to the visited set. Is that making sense? Yeah. Can you speak up? Yeah. So this is I clicked on this link. Okay. Okay. Is that good? Okay. So I now want to modify it to not have this nested loop, because this nested loop basically means potentially go through every pair UV every time. So Python has an efficient implementation of priority queue. So the way it works is something like this. And then you can add items like this with the value and the priority. So I'll add so priority 1, priority 2, and then I'll get the lowest priority like so. So if I run this, hit push this. So so here I got the element with the lowest priority. So this could be a string as well. So what's like the lowest priority right now? Probably praxis is like lowest priority, which means highest priority, and calc is the other way, right? Or I guess not, it's like second place. So this retrieves priority calc. So if I were to push something that's even higher priority, that would be the thing that gets retrieved. Okay. So this is just the Python implementation of priority queue. Okay. All right. So now what I want to do here is, rather than do this kind of thing, I want to say when I add something, so this is current V being added. What I want to do is I want to go through all the connections of the one that just got added and add them to my priority queue of the neighbors to be considered. So I'll initialize. my to be considered as just the empty list. And here I'll go through all the connections. If it was already visited, then I'm done. Otherwise, I'll add it to the priority queue. So that was interesting because that was a bug that Copilot was suggesting. So the priority should be the sum, right? All right. So now I, of course, need the current. So what would be the current? Well, the current would be whatever I get from the priority queue, right? So I'll say current is this. Name it priority node or something. Let me actually, so one thing so here, this would have both the node and the priority. Let's just say this is the priority, this is current. And in fact, the priority is just the current distance, so I can just name it current distance. So this is just because you get the tuple back and you can unpack it right away. Okay. So the only thing that's left is anytime we do this, it needs to be the case that the queue is not actually empty. So to be considered initially should be the set of should be the set where the distance is 0 and the node we're considering is start. So that we don't need anymore. Let me just delete this. So here's the concept, right? So the concept is we have our priority queue to be considered. Initially, it's just the starting node. And then every time we visit the node, we look at all the neighbors of the node and push them to the priority queue, with the priority being the cost of the connection plus the cost of getting to this current node. This is actually so here, so this is the weight, and this is con node distance to start. Right. Is that making sense? Yeah. The weight of the connection is the cost. So we are the weight is just the number that's associated with the edge, right? So yeah, and con is one of them, right? So the way the edges are stored is as a list of nodes to which you're connected. So each con has the node and it has the weight. Sorry, this Sorry, this is, sorry, I was confused. This is, of course, current. Sorry, confused about that. Okay, so this was good. So we want the distance to current plus the distance to the new potential neighbor from current. Yes.
So each connection is between two nodes. So which of those two nodes are we assigning as, self dot node under the class com?
Self. So the way the connection works is a node has a list of connections, right? So each connection consists of node and weight. So that means the connection is to this node with this weight. So let's maybe make a graph in this format. Maybe that will make it easier. So I'll say, so like YYZ would be like node YYZ, and like LAX would be node LAX, and YUL would be node YUL. And then we can start doing connections here. So I can say YYZ, append, and then it's connect. So this would be a node. So maybe LAX and maybe YYZ to LAX costs 1,000. And then I can also append a connection to YUL, which is like 300. Yeah. Connections. Yeah. Thank you. That's right. Okay. So skipping back to the algorithm. So does the algorithm make sense? Yeah.
So would you be able to just briefly go over how the function works, like what the code is saying?
Okay.
The function.
Okay. So what we're doing is, so I think it's easier with the slide. So what we're trying to do here is we're trying to say, start a priority queue. The priority queue is the neighbors that we consider adding that are going from the visited set to some other node. The way we maintain this priority queue is we add every neighbor every time we visit a node. We look at all its neighbors, we add those to the priority queue, with the distance being, if I go through this node, what would be the cost to get to this neighbor? Maybe there's a cheaper way through another neighbor, that's fine. That would also be added to the priority queue. Okay. So here what we're saying is, okay, so get me the current, let's switch the code, I guess. So here what I'm saying is start this queue with start and the cost of getting from start to start being 0, right? Then I'm saying, okay, so get me the current node from the priority queue. So that means the node that's associated with the cheapest path from source to that node that hasn't been visited yet. Okay. So, okay, now visit it, and now go through every connection of that node, meaning go through every neighbor. And if that neighbor hasn't already been visited, push it to the priority queue, with the cost being the current weight plus the weight of the connection, rather, plus the cost of getting from the source to current. Yeah. So heap push is adding to the priority queue, right? So this is like this. Yeah.
Start at the end, and then like go to the next bit. Why do you still start at the start?
So I don't really start it either. So the connections here is just the list. It's not stored. It's stored. Actually, someone asked me before, like, why do you use the linked list? Why not just use like a regular array? And this is what we're doing here. So I'm just appending to this list here. So it's not like in the beginning or the end. It's just a list of those, just for simplicity. Yeah.
Set.
So set is the set of all the visited nodes.
What does set use in a function? Or like-
Oh yeah. So set, if you remember, is a way to. So we did it like very briefly. So set is something like this, and you can like go through elements of set, and you'll just get one of each.
Like a list.
Well, like a list, except with no repeats. So if you add the same thing to the set, the second time it's not gonna matter. Yeah.
So like that would be just typecasting, right?
We are not exactly casting, so we are initializing the set to just contain the node start.
We had a list there with repeated things. And we
Yeah. So like you create a set with the same contents, that would be just one of each. Okay.
would it just keep the first of each type?
And then not exactly the first of each type. Like the assumption here is like they're equal, so it's not like the first of each type. It's like one of each objects that are not equal to each other. Okay. Yeah.
It's like be like on like the people get like part of this
Yeah.
but part of it are not that you like part of this is like this is not the source.
That's exactly right. Yeah.
So are we immediately, oh, never mind.
Okay. All right. So that's the algorithm. Do you want to run through the algorithm, or is that okay? Yes. Yes. Okay. So let's do that again. So we are on this guy. Right? And now we have our queue. And initially the queue is 0, 8. Okay. So we visit A, and that means that we add to the queue B and C and D with their associated distances, right? So this got removed, and then we have C, and we have B, and we have D. Okay, so that's the queue now. Now, every time that, so now we say, okay, and record D of A as 0. Okay, now we get the first element from the queue, so that would be the one with the smallest priority. So that would be C. So we get C, visit it, remove it from the queue, and add its neighbors. So we've added E with priority 4. That would be in the middle, actually. Okay. Pop the next thing from the queue. So C got removed. The next thing in the queue is E. So how come didn't we? Wait, did I did have B here. So the next thing that we pop from the queue would be B. Like this. So D of B is 2. And add all of B's neighbors. So this is just E. So this would be 3E. So now E exists twice, once with priority 3 and once with priority 4. So then we pop this one. So that's going to be D of E is 3. And that goes away. And we add F and G, right? So F is going to have priority 7 plus 3, so 10. And G is going to have priority 8. If something's already visited, we just ignore it. And now we'll pop D and so on. Actually, so popping D might be interesting because that will add E again. Well, yeah, actually not because it was already visited. Okay, so we pop this. Say D of G is 6. D is what I meant. And then we'll pop G and add H. And add the neighbor. And then we'll just get F and H. Yeah.
Oh, I'm.
No, it's not the list of all unvisited nodes. It's the list of neighbors of visited nodes together with the distances via those nodes. Yeah.
Once you visit E, would you re-add it to E?
So like it's a question of where to put the E. So like if E is visited in our code, we don't add it because
Like once you put in E, do you add in the value of D with the DE with the value of 13? Oh, 11, sorry.
do you mean
Like,
H?
Into the cube. Because once you visit E, D becomes a neighbor again. So do you add that connection of 11?
Oh yeah. Oh, if I haven't done that, then yeah, you would. Yeah.
What happens if you pop E before you add in all of the nodes that have E as a neighbor prior to, and then there's actually a cheaper one there?
Then it will get higher in the priority queue. And that's the magic of it, right? So like you add a node and you add all its neighbors together with the associated costs.
Oh, is that? Oh.
Yeah.
But Q is just to be considered, right?
So it's to be considered in the order in which it's listed by the priorities. Okay. Yeah. Yes, you could. Yeah. Yeah, so you need to check whether it was visited before you visit it again. Yeah.
Sorry, just go back to my question. Basically, because you know you haven't. Okay, it's okay.
Okay. Yeah.
Saying, but no, like, when we opt the E.
Yeah.
What was the 4E removed?
No, it's not removed. It's just that so you need I think I didn't add so like you do need to explicitly say, and I might not have, that if you pop it, then we need to skip it if it's already visited.
Later, you said like the add E again if we go to D?
That's possible. Yeah. So we ignore it twice, right? So like if if we see a connection that's already been visited, we just don't add it. If you pop something off the queue that's been visited, you just ignore it because it's already visited. Cool. All right. So that's Dijkstra. So I want to now at least start talking about kind of other graph search algorithms. That's going to take like probably 20 minutes. So for now, I'll just show you pictures. So here is it's a cool picture. Here is a picture that's also graph search. So if we are talking about walking on a grid, you could imagine thinking about it like that. So basically imagine that you have this grid, right? So you are allowed to walk on the light squares, but you're not allowed to cross the dark squares. So one way to think about it is you could say, this one is connected to this, and it's connected to this, but it's not connected to this. So if each node here represents a square, you can make it so that this is connected to this, but there is no connection here, for example. Okay. So that's the setting. So here, so we were talking about cheapest paths. Here, every edge just costs 1. So if you're looking for shortest path, you're just looking for a path in this graph, which is, as few edges as possible. So here, let's disallow diagonals. And here so let me paste this link in here. So if I disallow diagonals and I do the search, so I'm trying to get from the green to the red. And here I'm doing Dijkstra. This is how it's going to go until I get to red. So not super efficient. So here the blue are the visited ones. And then finally I find the shortest path from green to red. Right? And the reason it's like that is the way we're doing the search is we're considering every possible neighbor of every possible neighbor of every possible neighbor. So you kind of see how the neighborhood kind of grows in all directions, right? So you could also imagine doing breadth first search. So again, I'll disallow diagonals. And that's going to look almost exactly like that, except it grows like that. So we're basically saying, like, look at everything that's a distance 1, everything that's a distance 2, everything that's a distance 3, everything that's a distance 4, and so on. So that's going to look like this. You can also say, well, this looks silly, right? Because what do you actually want to do? Well, actually, you probably want to say, as much as possible, I want to go to the right. And if I get below the red point, I want to go back up. So if I see the red just geometrically on the page, I can say, well, just like look at the distance between where I am and the red and try to make the distance smaller rather than just looking at like what's the cheapest to go from green to anywhere. So that's essentially best first search. So not allow diagonal. So this is going to just say, okay, I'm just trying to get to red. And if I can make the distance to red smaller, I'll do that. If I can't, I'll do what I can. So that's going to look like this. And as you see, it's much faster. The actual, under some conditions, optimal algorithm to do this is A star. And A star is basically, you'll see, I guess tomorrow, is a combination of trying to get to red as fast as possible while doing something like Dijkstra. And that looks like this. So we'll see how to do that tomorrow, right? And then we're going to do binary search tree, and then we're going to do AI. Yeah. Say again?
That's what we also have to do before the crack out of all the optical crap, or just before the crack now out.
So A star and so A star has so like in general you can't find the optimal, but under some condition A star is guaranteed to return the optimal. So of course, like Dijkstra by definition gets you the cheapest path. It's just that it takes a long time. Best first is generally not guaranteed to get you the shortest one. So we'll do that in more detail tomorrow.